Today's topic is PECTA, Power Electronic Conversion Technology Annex, which is a project driven by IEA, International Energy Agency, which is a project aiming for more efficient power electronic converters, and it points strongly towards wide bandgap technology's potential. Phase 1 of this project is now completed, and that is the main part of this seminar today, to give the results from phase 1, but also to give phase 2 perspectives in the project. This is our first seminar on PECTA activities and results. We plan to inform on news and results from PECTA regularly, might be yearly, we'll see, as the project proceeds. Mitek, I lost the screen now. Can I get the agenda? For the ones coming in late, thanks. Please turn off your mics and videos. So this is today's agenda, short welcome from me. Then we'll have an introduction from Hans-Peter Nee, Peter Benich, which is in the PECTA project and has been from beginning, will give a background from on the project itself and it's where it's targeting. Peder Bergman will then give a presentation on the results from phase 1, which is documented in a quite extensive report, which is by wide bandgap technologies, efficiency, potential, and application readiness map. This will be followed by a discussion, which will be moderated by Carl Michael Zetterling, and I would give you some questions to think over and that we will discuss during this part of the seminar. That is, how can we make this switch to wide bandgap technologies go faster? Which are the opportunities or the barriers, and also is there a need for policies? And after that, we'll have a quick summary.
So, in order to reduce the CO2 emissions, we need electrification, and it's really one of the essential concepts we should concentrate on. And when I talk about electrification, it's not about producing energy like wind power, solar power, or also, as you can see here, geothermal power, which can be forgotten. But if you look at solar and wind power, so power electronics is extremely important, but it's also in the user environment where we will need power electronics, for instance, in electric cars and trucks and buses and so on. But there are many other industrial processes also where we can move from, for instance, hydraulics to electrical systems. And in all these cases, this will give us an enormous efficiency improvement. And the first point I want to say here is that wide bandgap power electronics is efficient. It can be made extremely efficient. At the bottom of the slide here on the left side, you see an inverter which we made at KTH. This one has at full power 99.6%, and at half power it has 99.75% efficiency. So it's not 97.5, it's 99.75. So these efficiencies are possible with wide bandgap electronics. This is silicon carbide. Now, why could we get so efficient conversions? Basically, if we take silicon carbide, we have 10 times higher maximum field strength. This means that we can make our PN junctions much thinner, or the drift layers, so to say. and also that we can have much higher doping levels. This boils down to a Baliga figure of merit of around 1,000, which means that we get 1,000 times less resistance in the on state. So we're not talking about small improvements here. These are massive improvements. However, when you compare now, let us say, a silicon IGBT with a silicon carbide MOSFET, you're not comparing the same kind of device. When we compare now silicon carbide MOSFETs with silicon IGBTs, we don't have a factor of 1,000 in difference because we're comparing two different types of devices. The silicon IGBT has injection of holes also, which modifies this comparison. However, because we put this extra P layer to induce holes, we also get an extra diode voltage drop. So on the top right, you can see a comparison of what the voltage drop looks like as a function of current. So we have this extra diode voltage drop in the silicon IGBT. This means that if we, for instance, compare now, even if we would have the same losses at full load, at light load, so let us say if we have half the current, we only have then 4 times lower losses in the silicon carbide case. We wouldn't get that in the silicon case. This also means that part load operation in silicon carbide, for instance, is much better than with silicon. We could also maybe make a design where we could take some overload in silicon carbide, and in the normal operation, then we would have very high efficiency. But we don't only see improvements in conduction losses. We also see improvements in switching losses. And if you want to turn off an IGBT fast and so on, the current will have a tail. And that's because we need to remove those excess charges we injected before from the P layer. This takes time. It also takes time to get all the charges in when we turn on. With a unipolar silicon carbide MOSFET, you don't need to wait for the current to turn off. You can take the voltage on the gate down quickly. The device will also turn off quickly. And practically, there is really no limit to this. The problem is just to get the power into the gate. And it's not trivial, but it's possible to switch extremely fast. And we have been looking at switching times now of the order of 5 nanoseconds or so. And this is possible. I don't say it's easy. So if you now look at the bottom right picture, this is a presentation from Toyota, which I've stolen. They looked at what they could do with this technology, and what they came up with is that all these things reduce the size by 5 times. And if we can reduce the size by 5 times, this means that we can space, for instance, in a vehicle. It also means that it will be much lighter. And again, we will not only save energy on that we have more efficient conversion. By making things smaller, we will also get things which are lighter. And in a vehicle, for instance, this means that we don't need to carry around and break a heavy weight. And this gives us an energy reduction. Also, if we have a much more efficient system, we could have less batteries on the vehicle, and less batteries again means less weight and also less energy consumption. So in many cases where silicon technology would not be competitive to make a transition like an electrification transition, with wide bandgap technology, this would be possible. So how can we speed up the transition? Because this doesn't go by itself. And the International Energy Agency wants to find the right ways. And we have an example here of LED lighting. So what we actually could achieve there. So not many years ago, we were still using old light bulbs, and now no one uses them. Everything is LED. And I think if it should be possible to do something similar by transitioning transitioning over to wide bandgap electronics. So the question is then, how can we translate this transition from LEDs, going from light bulbs to LEDs, to going from silicon technology to wide bandgap Polytronics?
So my name is Peter Bennick. I'm coming from the Swedish Energy Agency, subordinate to the Swedish government. And the question now is why should we care from the agency, the Swedish Energy Agency, and also the International Energy Agency? Why do we care about power electronics? So I tried to make a helicopter flight of why, and then zooming down, flying down to the PECTA, which is an initiative trying to promote and disseminate this power electronics based on wide bandgap technology then. So whenever I speak about what we are doing and why, I always start as high as possible. And I'm sure you know about this, but if you don't, it's probably a good idea to read and refer to this whenever you speak with a governmental person and asking for money. So 5 years ago, two things happened. One thing was the development of the Sustainable Development Goals, or Agenda 2030, where you have 17 groups of targets, from no poverty down to partnerships for the goals, collaboration among or between regions and nations. And there are 169 sub-goals under these. And you can see it's about everything really: affordable and clean energy, climate change, water, whatever. So it's very, very important framework now to refer to what we're doing and setting up the goals, and from there also discussing policies. And in parallel, of course, we have the climate, the Paris Agreement from 2016, basically, where governments around the globe committed themselves to limit emissions to maximum, to a level corresponding to maximum 1.5 degrees increase of temperature, something about 450 parts per million. Right now we have 420. The carbon dioxide budget is very low, 300 gigatons or something, meaning we have very little time to go to manage this goal, or to not hit the roof, if I put it like that. So this is a very important framework, so refer to that. Then each region around the world are trying to break that down, and you probably know about this for EU. The EU goes to 2030. We had goals to 2020 before. So this is addressing the supply of energy, trying to increase the share of renewable energy here. And then to 2030 says at least 32% should be renewable. And I mean, basically should be 100% eventually. I don't discuss nuclear power, but should be fossil free anyway. And then the end use here, this is also a separate thing, but in parallel, that we improve energy efficiency, because right now we're wasting a lot of energy. Just becomes heat, and we are using a lot of material also, and we don't have a circular loop. So here's a lot of things to do also. So it's supply and it's end use going in parallel like sisters or siblings. And these two together then will see to that the reduction of CO2 emissions are met on. And I don't know if you followed the discussions in the EU Parliament before Christmas, but this was actually 40% until Christmas, and then they increased this. And we expect this to be increased even more because there are a lot of discussions now. We are lagging in the timetable. So you have the goals, and then you have a range of policies to achieve these goals. That's the whole idea. So you had them on the EU level, you had them in US, you had them in the different regions, and you also have them sometimes on the national level. So it's very, very important to understand this framework. Right now, we have the Green Deal and the Green Recovery, as you might know, from COVID. So this is also addressing now also these things. It's not just about business and getting people back on track. It's really very much about these things too. It's also a job creator. So it's good to know about this if you didn't already. So what about then the IEA and this? So very quickly then, for those of you who doesn't know what this is, the IEA was formed in the 70s because of the oil crisis at that time. So from the beginning, it was really about managing oil supply and storage across the globe. But since then, it has widened its scope, so now it's doing a lot of things. Energy security, statistics, have a lot of fantastic reports promoting energy efficiency. Renewables should be here somewhere too. So it's a lot of things going on down there. They are based in Paris and doing a lot of good stuff. So check their homepage if you haven't already. A lot of good reports there. And then, as a side thing, we have what's called the Technology Collaboration Program. That is, it's related to or under the umbrella of the IEA, but it's actually independent programs. So member states and the IEA can get together and run programs on various topics. And here you see some of the topics here. And then if you scroll down here, you can see buildings. It's like themes here. You see a lot of things here. And then suddenly energy efficient end use equipment shows up, which is the TCP under which PECTA belongs. So typically this is where experts can meet. It can be universities, it can be other experts meeting together and doing things on behalf of governments. So we have a better basis for decision making. Then if you now zoom into the PECTA and the 4E, so this is then a program in itself, energy efficient end use equipment. And you can see there are 14 countries from across the globe working together. And what it's a little bit special with this one is that it's really policymakers and design experts meeting together and discussing both the technology per se, market assessment, technology assessments, and etc., and then also discussing policies. So me and my colleagues, some of which are in this webinar, I think, we are getting together and then discussing what can we do from the governmental side on the EU level, in US, in Japan, to address this. So we have the power electronic conversion technology annex, but we also have 3 other here, solid state lighting annex, electronic device and networks annex, and then which might interest this audience, electric motor systems annex, very much about motor drives, and then a lot of things on the policy side and standardization work. So if you're interested, you can check out this homepage and you find information about all this. So the power electronic conversion technology annex was actually my colleague Roland Bruniger, who might be here, where the Swiss government understood that this might be something that could be something for government to promote. It seems to be very promising, but it seems to go slow. Dissemination goes slow. So we decided on, at present we are not that many countries, but we think this will increase to really understand, okay, what are the drivers and barriers? Why does it take so long time? It always do that, but in this case, what's the unique drivers and barriers for this then? Because if you understand this, we can then think about policy that can sustain the drivers and lower the barriers. And hopefully this audience can help out here to say to us, okay, we have a lot of good things happening here. We shrink the size, cooling is easier, blah, blah, blah. That will be important for some applications, but there's still a lot of barriers. Could be knowledge, it could be business models, it can be different things. So tell us what are the problems and what are the opportunities? Because if you understand this, we can then go here and design some clever policies. So what have we done so far? Very, very quickly. We had a phase 1, which was really a scoping period. We tried to understand what was happening. And here there is a report. Peter Bergman will discuss the main findings from this report. But it's really like what are the technologies, applications, what are the saving potentials, and what we call the application readiness map. How far have different technologies and applications really come? And this, I mean, normally for us, energy savings are very, very important, but there could be other drivers too, and we are very interested to understand what those are, what these are. So that was phase 1. Then what we are writing now is a phase 2. So very, very quickly, just this is, you don't have to bother so much, but we are engaging experts from various countries in different tasks. I come to that in a second. Where we sort of have a discussion and explore these different themes here. We also have an industrial advisory group and an academic advisory group. And then we have some administration here. This is really me and my colleagues and the operating agent. Marcus Makasic, also on this call, I think, to manage the whole process. So the idea is to meet and discuss and explore and try to pinpoint what is really important here. So what we are planning to do now, and have started slowly but surely, is 6 tasks. Also discussing 7th here, and I can go through them very, very quickly. So task A here is trying to update efficiency figures from different applications and so on. Again, very important for policymakers. A second thing, the circular economy aspects and circular economy strategies are now also very important. We can't have a linear business model. We have to have a circular. So in order to address that, we need to understand more about this. Production, user phase, recyclability, upgradability, repairability, all these things will be very, very important. So modular thinking, for example, can we replace a module, or do we have to throw the whole thing away? That would not be accepted. Typical thing for a policymaker to think about. We're also going to revise the application readiness maps. Might be something that is updated, needs to be updated, or there might be new applications we didn't think about 2 years ago. Then a little bit more about the task D, policy system, trying then to discuss, okay, drivers and barriers. Okay, what could we do then? Should we set a regulation with requirements? We do that for a lot of products, or should we have it's carrot and stick discussion. Where are the carrots and where are the sticks? Where should we go in as a policymaker? And also, should it be EU level, or should we try even to influence the whole world? I mean, this is an IAA thing, which is really globally, but we can start somewhere and lead the way, maybe in EU or in Sweden or in the Nordic countries. Another thing which is also super important is the standards. How do we actually measure efficiency, for example? Very, very difficult. Connects to this task, for example. Hansi just told us the efficiency can be so very, very high. How do you actually measure that? Is it calorimetric measurements, or is it just standard power measurements? What do you do and how do you do it? So standardization work is also very important and very cumbersome, of course, also. Measurements, how do you do it in practice? There's some lab work going on, and that is also very interesting and will be very important to verify performance claims. If I say my device is so very good, I had to verify that somehow. So it's also very important. I will stop there for a second, but I just want to go back very quickly as a teaser. We are discussing, but we just haven't really come to a conclusion. We discussed also like a global contest on the most energy efficient application using wide bandgap. I can come back to that in another seminar, but should it be charging stations, PV panels, or I don't know what. You can think about that. It's kind of intriguing in a way, I think. So here are contacts. This is chaired by my colleague, Roland Bruniger, representing Swiss government, and Adriana Diaz from Austria, representing government there. So, and we also have Jacob Wolf Anderson from Denmark, and myself, and also run by our very good operating agent, Marcus Makasic.
Well, as Hansi and Peter said, I will give a short summary of the first phase of the PECTA work, which resulted in a publication and a report for the first phase, which can be found online, regarding the efficiency potential and application readiness maps. And the full report can be found on the EIA 4E webpage using this link. As Peter said, the first phase was focusing on looking at what areas for power electronics where we can find energy savings using wide bandgap power electronics. So we has been looking into the different applications, the advantages of wide bandgap applications, and potential energy savings. Another part in phase 1 was to look at what activities is going on, what roadmaps is underway to see or to predict how the wide bandgap power electronics will continue in the future. And for this, this resulted in what we call the application readiness maps, where we try to summarize the present status and the expected future progress of wide bandgap power electronics. And I will briefly go through these different parts of the report. I will not do it in detail, but just an overview. And I will end up with the challenges that we summarize in the report that will be partly as a basis for the discussion following. So in the report, we consider a lot of different applications where power electronics is important and where we can have strong influence on wide bandgap power electronics. This goes from road transport, railway transport, all the way to wind energy, photovoltaics, power supplies, energy distribution, and data centers. What we found out, and which I will come back to later, is that the dominant market for wide bandgap power electronics, and this we believe will be the market that will drive the development of devices, that will drive the volume, that will drive the cost, that will be the road transport, and especially the automotive personal vehicles, which are rapidly increasing and very large market. Since PECTA is interested in energy savings, we also identify other areas where we found a large possibility for energy efficiency. That was for wind energy, for photovoltaics, and for data centers, where the change from silicon-based power electronics to wide bandgap power electronics could have an important, or will have an important effect on the energy efficiency and the energy savings. Yes, such a background, which maybe is well known for most people, is what are the advantages of wide bandgap semiconductors. And when we talk about wide bandgap material, we are today talking about silicon carbide and gallium nitride. There are also other wide bandgap materials, but which we believe has a much longer time to develop into a real possibility in applications. So it's mainly silicon carbide and gallium nitride, and silicon carbide is the dominating material. The advantages are related to the very strong bonds that we have in the silicon carbide and also in the gallium nitride bonds. This gives both very high bandgap and also other properties such as high critical field, high thermal conductivity, high operating temperature, and blocking voltages. I would also like to say that the advantages of the wide bandgap material are also in some way a disadvantage when it comes to producing the material, to process the material, which influence the cost of the wide bandgap material as compared to silicon. The main device for silicon carbide is, as Hansi mentioned, the silicon carbide MOSFET, which will be competing with mainly the silicon IGBT. And the advantages for the silicon carbide MOSFET is then low conduction losses, low switching losses, high operating temperature, and the possibility to use both the MOSFET as the switch and a diode. This gives the possibility to use silicon carbide with higher power densities, higher efficiency, frequency. It can make, as Hansi said, smaller designs, not only more energy efficient, but also smaller in size and weight. And it can operate at harsh environments, more difficult conditions. For the nitride device, the nitride is not comparable to the silicon equivalent. The nitride device for power electronics is a high electron mobility transistor, where the active part of the device is a 2D electron gas and not an inversion layer like in the MOSFET and the IGBT. And the advantage of the gallium nitride HEMT for power electronics is a very low gate charge, low threshold voltage, and a low drain source on-state resistance. This gives the nitride power electronics very good possibilities in applications for high switching speed, which will give a reduction of passive, it gives smaller die size, and it also have the possibility to integrate with silicon carbide, no, with silicon technology. So, yes, one of the example of the estimate we made from switching from silicon to wide bandgap power electronics in different areas, we found that the total energy saving with a complete shifting from silicon technology to wide bandgap would give energy savings in the order of terawatt hour per year for laptops and cell phones, for photovoltaics, for wind power, for new battery electrical vehicles, and for data centers and large computer centers. So this is just an estimation of the energy savings we can obtain using wide bandgap materials. Another example is if we're looking into details for the main application, which are the automotive or the personal vehicles. In a automotive, wide bandgap power electronics can be used and are used in many different places. From the charging, which can be from the infrastructure, it can be on board on the vehicle, or it can be inductive from the surrounding. We have the internal DC-DC converter, we have the traction of the motor, and in all these places we can replace silicon with wide bandgap semiconductors. And an estimation, which is now a few years old, gives that we have a total efficiency by replacing the silicon power electronics with close to 18% if we do that completely in all the structures. When we started the work in the PECTA phase 1, we found that there are several ongoing roadmaps discussing the advantages and the future possibilities of wide bandgap power electronics. And this includes the European Center for Power Electronics, the ECPE, which has since many years has a roadmap labeled Roadmap Lead Applications for Silicon Carbide and Gallium Nitride. There is also, since many years, an ongoing activity within Power Americas, which published the roadmap last year with the title Strategic Roadmap for Next Generation Wide Bandgap Power Electronics. There has also been quite a lot of work between IEEE Power Electronics Society, which is called ETRV, International Technology Roadmap on Wide Bandgap Semiconductors. Also in China, has presented and published online a roadmap for the future of wide bandgap semiconductors. And there are also commercial roadmaps, and I will present some of the research from the Yule roadmap that was presented end of 2018. The Acme Roadmap has been made together with a lot of European industry partners and competence centers. This includes both universities and research centers. And they have looked at different applications, 28 different applications, and made a prediction for the status today. This picture is from 2018, but the final report was made 2019. And they have looked on the different applications for the different introduction of silicon carbide and gallium nitride in comparison to silicon, and divided that into where demonstrations are available, where they have a small market share, where they have a major market share, and finally where the different technologies have a dominant market share. And this was made by at the present state for the year 2025 and for the year 2035. So this kind of estimates for the application are made for all the different applications. To summarize, they identify, as I already said, that the automotive will be the dominant application for wide bandgap power electronics, followed by railway, photovoltaic inverters, large drive, industry automation, grid, and data centers. The Power America, which is a competence center for not only American or US companies, also provides education and funding for different projects. The roadmap and the publication is very technical. It's comparing their device performance and also cost and cost per ampere. And they focused on a 5-year roadmap to reduce the cost for the wide bandgap technology, to improve reliability and quality, enhance the performance, and strengthen the power electronics ecosystem, which includes education of personnel, of electronic designs, and so on. A summary of their roadmap is very difficult because it's very detailed, but I have chosen to select estimation of the market share for gallium nitride, power electronics on the left, where the scale here is million US dollar, and the same for the silicon carbide based expected market share. I could also say that this graph is used by several roadmaps and have been produced by a commercial company. And as we can see, there is a drastic increase of the use of both nitride and silicon carbide, both for today and expected in the future. As for the Acme roadmap, the automotive is divided as the main driver, followed by photovoltaics and information and communication technology and data centers. The ITRV, as I mentioned, published the roadmap last year, and they focus on 4 different points. That is to share the R&D progress and to identify opportunities and bottlenecks. They try to identify the most effective path for the technology development, and they want to develop technology-specific contact within different working groups, which then has contributed to different parts of the roadmap, and also to create a reference framework. In this roadmap, they was in similar to the other roadmaps, looking at short term, which are from now to 5 years, medium term 5 to 10 years, and long term, which are longer than 10 years time scale. The main application is, as already mentioned, the automotive, which includes both traction drive and charging for electrical vehicles, and also photovoltaics and traction drive for trains and power supply. The ITRV are more optimistic about the gallium nitride power electronics for lower voltage as compared to the other roadmaps. Finally, for the roadmaps, I would like to show the market expectation from Joule. For those of you who don't know Joule, this is a commercial company who is doing analysis and roadmaps in different technology fields. They're also comparing devices and doing reverse engineering and selling reports. They have been active to forecast the silicon carbide market for a long time and has been, for many years, been very optimistic. But in recent, or maybe too optimistic, but in recent years they have been able to quite good predict the increased market for silicon carbide. For the gallium nitride market, they are a little bit more uncertain and has two different scenarios. One is a positive one where gallium nitride will take a market share, but at a slower pace as compared to silicon carbide. Another scenario is that gallium nitride will not be an important technology for power electronics, mainly because the cost issue as compared to silicon. So to summarize the different roadmaps that has been presented during the last year, is that all roadmaps foresee a very drastic increase or very important increase in the use of wide bandgap power electronics, especially for silicon carbide, but also for gallium nitride. The main driver, both regarding volume and price, and also the availability of different devices, will be the automotive application for personal vehicles. This application will increase the volume, which is already happening. That will decrease the price, and this will also be beneficial for other applications who can use the larger amount of available devices at lower prices. For the wide bandgap technology, the roadmap foresees the following simplified scenario for silicon carbide and gallium nitride. For low voltage, that is up to 650 volt, gallium nitride is the most possible application, but with a cost competition with the silicon carbide and the silicon carbide MOSFET. For the medium voltage, which are in this case 650 up to 3.3 kilovolt, the silicon carbide MOSFET will be the main technology in competition with silicon and silicon carbide hybrids, meaning that it could be silicon carbide diodes and silicon IGBTs. Also for higher voltages and high power, silicon carbide MOSFET will be an important technology in competition with silicon IGBTs. For high voltage, this means above 6.5 kilovolt. Most roadmaps foresee that the silicon IGBT and other device solutions will dominate for a long time, but maybe that silicon carbide IGBT can be a possibility on a longer time scale. And this is mainly due to the cost of large area silicon carbide devices as compared to silicon devices. Based on the different roadmaps, the report that we made in phase 1 in PECTA has resulted in what we call the application readiness maps, or ARM, where we summarized the today's situation and also the expected situation for 5 years and 10 years solution. So to summarize, today we see that mainly silicon carbide MOSFET are used in many applications in the range from 650 to 1.7 kilovolt. As already mentioned several times, the dominant application is the electrical vehicles, where silicon carbide is used both for traction inverter, DC-DC converter, and for battery charging. And one of the milestones or the increase in the demand for silicon carbide was the decision by Tesla to use silicon carbide in the Model 3, which gives lower losses, but also, which was very important, that using the same battery structure, we get a longer driving range for the Tesla using silicon carbide technology as compared to silicon. And the driving range is a very important parameter for especially the US market. The fact that Tesla chose silicon carbide was also important, since Tesla is a very popular and hype technology, and that has made many other automotive manufacturers also starting to look and starting to use silicon carbide in the power electronic solutions. The use in automotive is also important, since, for example, in Tesla Model 3 uses between 50 and 100 transistors, and since they are producing more than 100,000 cars per year, this gives a very big volume demand for silicon carbide, which has been the driving force for the expansion of the silicon carbide. Also, for railway traction for higher voltage, silicon carbide MOSFETs are today used in the Japanese New Japan Railway Shinkansen latest model that was presented last year. In this case, the silicon carbide MOSFET can make different solutions to reduce the size and volume, which has made it possible to redesign the motor drives and the cars because of the smaller area and weight required for the power electronics. Today, power photovoltaic applications are also using silicon carbide in medium and high power systems. Today, there is also, due to the increased demand, there is a big shortage of silicon carbide devices and material. And due to this, and due to the expected large increase in demand, there has been in recent years presented large investment plans from many material and device suppliers, including Wolfspeed, ST Microelectronics, Infineon, and Rohm, to increase the capacity for silicon carbide. On a longer time scale, all roadmaps foresee a large increase in the demand for wide bandgap power electronics. This, combined with more aggressive plans for a general electrification from the automotive industry, based on the reduction of CO2 emissions, as described by Peter in the previous, this will give expected large demand and increased volume for especially silicon carbide-based solution, and reduction in cost is expected, since there will be an increased production, and both regarding the material growth and the processing, which will make silicon carbide more cost effective. From the automotive electrification on the personal vehicles, this will also expand into heavy vehicles such as trucks, buses, and specialized vehicles. The main device will still be the silicon carbide MOSFET in the range of 650 volt to 3.3 kilovolt. On a longer time scale, it's more difficult to estimate or predict what will happen, since they are depending on many factors. For example, how fast the electrification of the automotive and the rest of the transport sector will be. It will also depend on future political initiatives, such as the Green Deal from the European Commission, and also the green recovery that is a result of the corona pandemic. That was not an issue when we started to write this report. But these decisions and also decisions from, for example, IEA about policies and regulations. The silicon carbide power electronics will or is expected to be a dominant technology for many power electronic applications, especially for the automotive. The same is the case for data centers and information and communication technology for higher voltage, as well as for railway, wind power, and large drives. For the gallium nitride, the application readiness maps see that the gallium nitride power electronics will mainly be used into voltages up to 650 volt, but at a smaller volume that is expected for silicon carbide. The present application for gallium nitride is in automotive for DC-DC converters and chargers, and they can also be used in industrial inverter drives for power supplies in data centers, but at a lower voltage range. The quality and maturity of the gallium nitride technology is still not as developed as for silicon carbide, but with time and when the technology will be more mature, it could also expand into the applications where now silicon carbide is used in the 650 volt range. One possible application that could be very important for gallium nitride is for data center up to 650 volt, and also household supplies and chargers, which is now dominated by silicon solutions. Gallium nitride will then have the possibility by using higher switching frequency and lower losses to give higher efficiency in applications as compared to what is obtained by silicon today. This is also an application with a large volume with many units and with the possibility of good energy efficiency, which are one of the goals of the PECTA. I will not go into detail, but in the report, the expected progress has been summarized in different graphs, similar to this, which is showing the automotive and railway, where in different applications, the use of different technologies, for example, silicon carbide and gallium nitride, has been estimated from today or from last year until 10 years or 15 years in the future. This has been made both for the application areas and also for technology areas. In this case, for silicon carbide 650 volt, where we have summarized where and how silicon carbide MOSFET for 650 volt will be an important player in different applications. Another example is the higher voltage 1200 volt silicon carbide MOSFET with the time scale and the different applications. And finally, the gallium nitride HEMT transistors in power electronics with a timeline for different introduction of these devices into the applications. Finally, I would like to go through some brief technology challenges we see for wide bandgap power electronics. And that is, for example, temperature increase, the possibility to use higher temperatures, which also increase conduction losses and give problem with interface and insulation that needs to be solved. We have, like all new technologies, the issue of reliability. What about long time failure mechanism? that this is something that is a question and that needs to be developed. The high switching speed for both for silicon carbide and for gallium nitride give high impedance and can give challenges with electromagnetic interference. We need to develop, or the market or the companies need to develop new package solution to utilize the higher current, the higher temperature, and the higher frequency, and also to improve passive components, magnetic and the electric components, and maybe look into more material with lower temperature coefficient to avoid stresses due to the higher operating temperatures. Cost is an issue for wide bandgap semiconductors and will be an issue. It will always be compared with the corresponding silicon technology, which will also develop in time, and the cost issue will be important. Us will the shortage of material. I mentioned that today there is a shortage of both material, processing, and testing, and this will need to be solved in the future to be able to use wide bandgap material in all applications that have the possibility. Finally, which is a big part of PECTA for the phase 2, standardization, both for wafer material, device, modules, and packaging, standardization in power measurements and efficiency measurements, and also the life cycle analysis to, on the long term, reduce the impact of the technology on the energy consumption and environment. So with that, I will stop.
Many of you have been in contact with me to get the link to this meeting, and feel free to contact me in any other questions about this meeting. We will try to publish the slides via the IEEE link that we originally had the presentation on. So if you don't find the slides and recordings later, don't hesitate to contact me or Meetic. So coming back to the solid state lighting, what we learned from that is that we can achieve energy efficient lighting that surpasses traditional technologies. We can get lower energy consumption and environmental savings, but for the case of lighting, we found that policy change was needed to really get consumers to switch over to get a large volume production of LEDs and to reduce the cost. Actually, I saw it was in the news today. Dagens Nyheter brought up this article from 2015, the lighting paradox. Cheaper, efficient LEDs save energy, and then people use more. Oh no. However, the calculations are not as, if you go through it, you find that even if you save 10 times, if you use a tenth of the energy for your lighting, and then people use more lights, it's not going to eat up all of that power savings, because who's going to put 10 times the amount of light in their home anyway? But I think more important is to talk about the switch to wide bandgap power electronics and what we can do to promote it. Because energy savings is not always as large. It's not like the factor of 10 for incandescent lighting. It's more like a factor of 2. The good news is that the switchover cost can be smaller. There are silicon carbide MOSFETs at about the same price as silicon IGBTs for the same ratings today. Other environmental or life cycle savings are not as obvious because silicon and silicon carbide devices are made roughly the same way. We're not removing mercury or other toxic materials from the production. But I think, as Hans Peter showed, there are other applications that will then improve our use of natural resources. And the positive signs I see for wide bandgap power electronics is that there are multiple manufacturers to second source your components, so you can design them in. There are also good evaluation kits and reference or demonstration designs out there, even up to 15 kilowatts, to help you start using wide bandgap semiconductors. If you look around, there are also webinars on circuit design and gate drivers for the wide bandgap electronics, since there are some things you need to make different for driving silicon carbide MOSFETs. There's also a discussion about reliability, not just about passing the simplest tests, but also looking at early and late failures. So this is a link to a discussion about this. So for our discussion now, let's think about what's next. How can we speed up the use of the wide bandgap technology's potential? We've heard of some opportunities, but are there any barriers? What need do we have for policies? Any suggestions?
First of all, I would say like to say thank you to all the listeners and to the presenters, Hansi, Peter, Peder, and Carl Mikael leading the discussion here. We had some incidents on the presentations in the beginning, but I think it's sorted out quite well. And I won't be long here. Conclusion is that wide bandgap is an important technology which can be used for CO2 reduction and electrification. PECTA is a mean of speeding this up and might be doing more to implement energy savings using wide bandgap technologies. So that is a very short discussion and summary. And from the discussion, my take is that it's a good pace on components. We need to do more on system aspects, how to use this component in a system to get all the full potential of the technology. And there are, for example, operating at higher temperatures, operating at higher frequencies to make smaller systems, and by that save on material and energy. That is what we need to do in the near time to accelerate. So that there might be some opportunities to do more research to more speed up the transition. And from the high number of participants in this seminar, my takeaway is that there is a great interest to follow this, and due to that, there will be new invitations for seminars like this, spreading information about results and perspectives of PECTA. When coming now, starting to work in the phase 2, might be that's half a year from now or a year from now when we can have the next seminar. You'll get invited. And by that I conclude the summary, and I